Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about linear estimation. The goal is to derive the optimal linear estimate of a quantity given another quantity. The prerequisites for this material are multivariate distributions, averaging, and correlation. We actually have already solved this problem of determining what the optimal linear estimate is in terms of mean squared error for standardized random variables that have zero mean and unit variance. In a previous video, we established that the best linear estimate of B given A in terms of mean squared error is obtained by multiplying A by the correlation coefficient between A and B, which just corresponds to the expected value of the product between A and B. But this only holds for quantities that have zero mean and unit variance. We also talked about non-standardized random variables, where the mean was some arbitrary number, so mu A and mu B, that's how we denote them. And the variance can be different from 1, so here we denote it by sigma A squared and sigma B squared. In order to quantify the linear dependence between these random variables, what we did is we defined the correlation coefficient between them as the correlation coefficient between the standardized random variables. So we determined that the best linear estimate of S of B, the standardized version of B, which again is obtained by just centering and normalizing, is obtained by scaling the standardized version of A by the correlation coefficient. Now we're going to think about how this translates to estimating B from A. So what is the best linear estimate of B given A? We can actually write B in terms of its standardized counterpart, S of B. All we need to do is scale by the standard deviation and add back the mean. So if we have a good estimate for this guy, for S of B, then we can just plug it in there, right? So a reasonable estimate for B would be taking so adding the mean plus the best linear estimate of S of B times the standard deviation. This seems like a reasonable estimate, and in fact, we're going to show later on that it is the optimal estimate. But before that, I would like to visualize a little bit what this means, okay? What this estimate of B given A is. So let's take a look first at a case where we just have S of B and S of A. So S of B, this is S of B and this is S of A, and we see that, well, we established that the best linear estimate of S of B in terms of S of A is obtained by just multiplying by the correlation coefficient. Now, imagine that the original random variables are not standardized. In particular, A is not standardized. And we want to think about the best linear estimate of B given A. Well, since B here is still standardized, then the best linear estimate should be this. We just need to plug in A there. How do we connect A and the standardized version of A? The standard S of A is just A minus its mean divided by the standard deviation. Okay, so now a reasonable estimate for B is just multiplying by the correlation coefficient. And what do we multiply? This function of A. This is going to mean that we're going to shift this line, which is the best linear estimate. I forgot to say that. So this line has a slope that is equal to the correlation coefficient. Once we adjust for the fact that A has non-zero mean and standard deviation that is not equal to 1, then this is how we should shift we should shift and tilt the linear estimate. Okay? Realize that this is really a linear estimate because it's a line that goes through the origin. Once we shift it in this way, it's not a linear estimate anymore. If you want to be a little bit pedantic about it, mathematically it's an affine estimate because we're adding a constant and then multiplying, then scaling. Okay, so this is just for you to visualize what is happening in terms of A, when A has non-zero mean and a standard deviation that is different from 1. What happens when it's B, that has a different mean and a different standard deviation? Well, in that case, we remember that we can obtain B from S of B by just summing, adding the standard, sorry, not the standard deviation, the mean, and scaling S of B by the standard deviation. Okay, we know that this holds. So essentially, we should just plug in the best possible estimate for S of B here. Okay, so again, we start with a linear estimate, but now we're going to shift it by adding this constant, which is the mean of mu of B, the mean of mu B, which is the mean of B, and we're going to scale by the standard deviation of B. So this again is going to shift. In this case, we're going to shift this line upwards by mu B, and we're going to tilt again due to this standard deviation. We're going to tilt the linear estimate to make it into an affine estimate. If we combine these two aspects, what we do in terms of A and what we do in terms of B, the estimate is still affine. It's a little bit complicated, right? Because first we center and we normalize A, and then we have to take into account the standard deviation of B and add back the mean of B. And essentially, it's a little bit complicated to follow exactly what's going on, but the main point is that from this linear estimate of S of B given S of A, we get an affine estimate of B given A. And what we're going to show now is that this affine estimate is actually optimal in terms of mean squared error. So hopefully this gave you some kind of visual intuition about what is going on when we translate from the estimate of the standardized random variables to the estimate between the actual random variables that are non-standardized. All right, so we want to find a scaling factor alpha and an additive factor beta such that when we scale A times alpha and we add beta, we obtain the best possible approximation to B. That's what we want to do. So first we're going to consider the additive, this additive constant, and we're going to remember that if you want to obtain the best possible constant estimate of a random variable in terms of mean squared error, that best constant estimate is equal to the mean. Okay, we established this earlier in the course. So now, if we take this random variable x to be B minus alpha A, we're going to very quickly see that the optimal beta prime for any value of alpha is just the expected value of this random variable, right? Because we have this random variable x minus a constant. The best constant that we can choose in terms of mean squared error is just the expected value of x. So this indicates that the optimal beta, the optimal additive constant, is equal to the expected value of B minus alpha A. It depends on alpha. In fact, it's equal to mu B minus alpha times mu A. Okay, so depending on alpha, this is going to change, but it's always this function of alpha. So we can just plug it in to our estimate. And that's exactly what we're going to do. Okay, we're going to go back and we're going to plug in the best possible beta here because we're minimizing with respect to mean squared error. You cannot do better than this beta, so we're just going to plug it in. When we do that, we obtain this function because remember that this beta prime that is optimal is equal to mu B minus alpha mu A. We're basically centering the random variables. Okay, so you start seeing where this is coming from. Well, not where this is coming from, where this is going. That's what I meant. Sorry about that, where this is going. We have the centered random variables, so maybe now we just need to divide by some stuff to get the standardized random variables because we know what the best linear estimate of the standard random variables is, right? Like the standardized version of B given the standardized version of A. So we're almost there. So let's try to get all the way there. Again, we have subtracted this optimal beta, and now we only need to worry about alpha. We have the two centered random variables, so let's divide. We divide by sigma B and sigma A. Here we divide and multiply by sigma A. Okay, so we can do that. And in order to obtain a sigma B here, we just divide and multiply by sigma B everywhere, and we take this sigma B square out, and we're going to ignore it because it's just a positive constant. I have already said that if it turns out that the variance, I have already said in the previous video, I said that if the variance of B is 0, then B is just equal to a constant anyways. So the best linear estimate is just going to be equal to that constant. So that's not a very interesting case. We can assume that it's a positive constant. We can just take it out and then ignore it because we want to minimize this with respect to alpha. So it's the same as minimizing that multiplied by a positive constant. All right, so by multiplying and dividing by the standard deviations, we now have an expression in terms of the standardized versions of A and B, so we're pretty happy. Here we've done a change of variables where we've said minimizing this with respect to alpha is the same as, so minimizing all of this with respect to alpha is the same as minimizing all of this with respect to alpha prime, where we have made this change of variable alpha prime equals to alpha times sigma A divided by sigma B, okay? So now we do that. We do that. Basically, now we ask ourselves, what is the optimal alpha prime? Well, it's the scaling factor that we need to apply to this standardized random variable in order to approximate this other random variable. What is that equal to? We've seen in the previous video, is just equal to the correlation coefficient. And now we can obtain the optimal alpha through this change of variable. The optimal alpha is going to be the correlation coefficient, because that's the optimal alpha prime, times sigma B divided by sigma A. So now we're going to go back and plug it into the optimal beta prime, which was mu B minus alpha times mu A. So alpha times mu A is what we have to plug in here, and we've solved our problem. Now let's see what the actual estimate looks like when we use this scaling factor and this additive factor. Okay, when we're multiplying A by the scaling factor, we're adding the additive factor. And here what we realize is that this guy and this guy are multiplied by the same thing. So this is actually the standardized version of A multiplied by the correlation coefficient and then scaled by the standard deviation of B plus this constant. So it's exactly the same thing that we have obtained from common sense, realizing the connection between B and S of B. So when I presented this in class, a student had a very interesting observation, which they said, like, okay, you've told us this very long story, but couldn't we have just gone back here and just use derivatives to find the optimal alpha and the optimal beta here? Wouldn't we have obtained the same result? And the answer is absolutely yes, absolutely. It's just that I thought it was much more intuitive to start motivating this through the correlation coefficient by showing you that it's the scaling factor that you apply to the standardized variables and then connecting that to general linear estimation between random variables. But it's completely true that if we had just minimized with respect to alpha and beta here, we would have obtained the same result. Okay, so now let's take a look at some examples. In the previous video, we talked a little bit about height and rebounds in the MBA. Here, the correlation coefficient was 0.42. When we do these transformations that we need to do because neither rebounds nor height are standardized in general. Okay, rebounds, as you can see, go from around 0 to 12, and height goes from 170 centimeters to up to 230. This is the line that we get. That is the actual optimal linear estimator. Again, it's an affine estimator. I tend to say linear because that's what everyone says, but if you want to be mathematically precise, it's an affine estimator. Okay, that's the best affine estimator of rebounds given height. Same thing for assists. Once we correct for everything, that's the best linear estimator of assists given height. And this is the best linear estimator of points given height. And you see that the slope is not very marked, indicating that the linear relationship is not that strong. Now, it would be interesting to compare this linear estimate to the best nonlinear estimate. So let's remind ourselves what the best nonlinear estimate of a quantity given another quantity is in terms of mean squared error. It's actually the conditional mean, essentially by the same argument that we applied before, which says that if you want to approximate something by a constant in terms of mean squared error, the best approximation is the mean. If you want to approximate something given, this additional information, then the best possible constant, but by constant I mean function of this value A, is going to be the conditional mean of the quantity of interest given A. Okay, we talked about this in a previous video, but I just wanted to remind you of the intuition. If you want the best possible estimate in terms of mean squared error of B given a fixed value of A, then that estimate is the conditional mean. So let's take a look at how this compares for heights and rebounds. Realize that the conditional mean is actually going to be quite noisy when we don't have a lot of things to average over. So maybe let's think a little bit about the advantages and disadvantages of the linear estimate with respect to this optimal nonlinear estimate. A clear advantage is that the nonlinear estimate is noisier. Okay, it's unlikely, for example, that this is actually corresponding to true structure, like this is actually meaningful in any way. What is more likely is that because we don't have enough data and we're computing a lot of averages, we're going to computing averages basically at every possible height. If we don't have enough players, it's going to be quite noisy. Whereas the linear estimator depends on two parameters. We're computing two parameters from all the data. So many less parameters than the conditional mean. Here, the conditional mean, we're computing it for about, I don't know, like 25 different heights, maybe 30, so many more parameters. So that's an advantage of the linear estimator, okay? In general, it's going to be less noisy. It also allows you to extrapolate perhaps more easily to places where you don't have a lot of data. Arguably, right? We would need that to actually check this on test data to be able to say that with a clear conscience. Now let's think about the disadvantages of the linear estimator with respect to a nonlinear estimator. The disadvantages is that the linear estimator cannot account for nonlinear structure. So here we actually see that this looks actually pretty proportional for both estimators. But here for short players, it looks like height and rebounds are not as related, which kind of makes sense because these guys are all point guards. So maybe they rebound in similar fashion, like the relationship between height and rebounds is not as strong for this subclass of players. The conditional mean can adapt, right? Because it's just changing its estimate for each possible height. The linear estimator cannot adapt. Like if there's a strong linear relationship here, it's still going to think there's a strong linear relationship there. It doesn't have the flexibility to adapt. This is actually even more apparent where we consider height and assists. So when we consider height and assists, you can see here that between small players, it looks like assists are roughly constant, and this makes a lot of sense because these are point guards. And it's unclear that for a point guard, it's worse to be taller, right? Like you're going to give less assists because you're a taller point guard. If you don't know about basketball, point guards are the ones that kind of distribute, like create, they're the ones that pass the ball around to try to create scoring opportunities. It's unclear that for that kind of role, it's better to be shorter. Arguably, maybe it's even better to be taller. So if most point guards are here, it kind of makes sense why in this part of the plot you would have kind of a constant relationship between height and assists. The linear estimator is not able to deal with that. It's not able to account for that because it's not flexible enough. So that flexibility kind of is a disadvantage for the nonlinear estimate. When there's very little data, it becomes noisier, but it's a strong advantage when there's nonlinear structure, such as this one. Okay, in that case, the linear estimate cannot deal with it. Okay, and when we look at height and points, we again see that there's some noise in the nonlinear estimator, but we actually see that in general it does seem like this linear trend of shorter players scoring a bit more is actually also apparent in the nonlinear estimate, interestingly enough. Okay, so to finish, I want to remind you about some computations that we did about Gaussian distributions of Gaussian random vectors. We talked about random vectors, Gaussian random vectors, which were determined by, where the distribution is determined by two parameters, the mean, which is a two-dimensional vector, and this covariance matrix that represented, how this ellipse this ellipsoid was shaped in high dimensions and so on. In this case, it's an ellipse because it's in 2 dimensions. If we parameterize the covariance matrix in this way, then it turns out that the conditional distribution of B given A is Gaussian with this conditional mean. The important thing to realize here is that this is an affine function of A, and that affine function of A is exactly the same as we have derived, where we're standardizing by subtracting the mean and dividing by the standard deviation of A, and then we multiply first we multiply by the correlation coefficient. So this actually is another way to prove that this row here corresponds to the correlation coefficient between A and B if you parameterize the covariance matrix in this way. And then finally, we are multiplying by the standard deviation of B and adding the mean of B. So this is exactly how this is exactly the affine estimate that we have shown is the best linear estimator in terms of mean squared error. This shows that, and I mean, just in case this is not obvious, this is the conditional mean. So this is the best nonlinear estimator of B given A. In this case, the best nonlinear estimator of B given A is exactly the same as the best linear estimator of B given A. So for Gaussians, linear estimation is optimal. The reason is that for Gaussians, the relationship between the entries of a Gaussian vector is purely linear. Okay, this shows this. And you can see this also from the fact that the contours are ellipsoidal. Okay, so what have we learned? We have learned the definition of correlation. We have learned how to compute the best affine estimate in terms of mean squared error. And we have learned that linear estimation is optimal for Gaussian vectors. I feel that I have to come clean here. We have not learned the definition of correlation in this video. We learned this in the previous video, and for some reason I just left it there. Sorry about that, and thank you very much.